Section. Abstract. In recent years, we've seen a significant improvement in text-to-image diffusion models. These models can generate high-quality images from a text prompt. However, even the most advanced models sometimes struggle to follow the instructions in their prompts accurately. Most of these models are trained on datasets made up of image caption pairs, where the images are usually sourced from the internet, and the captions are the alternate text in HTML. A good example of this is the LAION dataset, which is used by Stable Diffusion and other models. We've noticed that these captions are often of low quality, which can significantly impact the model's ability to understand the subtle meanings in the text prompts. We've found that by relabeling the dataset with a specialized automatic captioning model and then training a text-to-image model on this recaptioned dataset, the model's performance improves significantly. For instance, the overall image quality improves, with a Frechet inception distance, a measure of image quality, of 14.84 compared to the baseline of 17.87. Human evaluation also shows a 64.3% improvement in faithful image generation. In terms of semantic alignment, we see improvements as well. For example, the semantic object accuracy increases to 84.34 from 78.90. Counting alignment errors decrease to 1.32 from 1.44, and positional alignment improves to 62.42 from 57.62. We've analyzed various ways to relabel the dataset and found that this technique, which we call recap, reduces the discrepancy between training and inference and provides the model with more information per example. This increases sample efficiency and allows the model to better understand the relationship between captions and images. In recent years, text-to-image generation models have made significant advancements. These models can generate high-quality and diverse images based on textual inputs. However, even the most advanced models sometimes fail to generate images that fully convey the meanings and nuances of the given text prompts. We've noticed that the datasets used to train these models often have significant issues. For example, the captions in the LAION dataset, which is used to train Stable Diffusion, come from alt.html tags. These tags are meant to convey the meaning and intent of the image, not necessarily a literal description of the image itself. We've observed that these alt tags often describe only a narrow aspect of the image, neglecting significant visual details. For example, an image of a person might have an alt tag that includes the person's name and the photographer's name, but not a description of their appearance, clothing, position, or background. We've also noticed that recent automatic captioning systems, such as Poly, produce highly accurate captions. This could be because the problem of converting images to text is easier, or because these captioning models are larger, are trained longer than the text-to-image models, or leverage large pre-trained language components. Based on these observations, we suggest a new method for improving text-to-image models by training them on improved captions, auto-generated by a custom image-to-text model. We call our method Recap, and we found that applying it to Stable Diffusion results in a model that performs better than the baseline in all areas. For example, the Frechet inception distance improves from 17.87 to 14.84, and human evaluation of successful image generation improves from 29.25% to 48.06%. In summary, our main contributions are a new method called Recap, which uses automatic captioning to significantly improve the quality of a text-to-image model, both in terms of fidelity and semantics. We also provide an analysis showing how the alt text captions used by current training methods can result in text-to-image models that often fail in fidelity and semantic alignment, and how different captions can mitigate these issues. Section Summary. Text-to-image diffusion models have made significant progress in generating high-quality images from textual prompts. However, these models often struggle to accurately follow all the directions in the prompts. This is due to the low quality of the captions used to train these models, which affects their understanding of nuanced semantics. By relabeling the training dataset with improved captions generated by an automatic captioning model, the overall image quality and semantic alignment of the text-to-image models can be substantially improved. Section. Related work. We're going to discuss the work that has been done in the field of text-to-image models, image captioning, synthetic multimodal datasets, and improving text alignment of diffusion models. In recent years, there has been significant progress in the development of deep generative models for generating images from text. The focus has shifted from using traditional methods to using autoregressive transformers and diffusion models. A key area of improvement has been enhancing the model's ability to effectively align with the input text. This is usually achieved by conditioning the image on the output of a pre-trained text embedder, typically a transformer. It has been shown that using a strong encoder significantly improves the alignment between text and image. Image captioning is a fundamental challenge in computer graphics. Recent models have made significant strides in this area, thanks to large-scale training data and the use of pre-trained image and text models. These advancements have enabled these models to tackle a variety of multimodal tasks. In our work, we fine-tune a model called Poly to recaption the training dataset of a text-to-image model. There are also some concurrent works that augment multimodal datasets automatically to enhance the capabilities of image captioning and embedding models. For instance, some researchers have shown that training on data with generated captions improves performance. Others have demonstrated how to improve a model called Blip by iteratively removing captions with high loss, replacing them with captions from the previous epoch, or generating a new image for them using a method called stable diffusion. Another important line of work is trying to correct text-to-image alignment issues in diffusion models. This is usually done by analyzing the input prompt lexically and modifying the attention maps throughout sampling. Some researchers have tried to prevent diffusion models from ignoring certain tokens by guiding the sample process to reweigh the token attention maps. Others have analyzed the prompt to identify modifiers and then used a sample time guidance to bind their attention maps to those of their entities. Our method, which we call Recap, consists of 3 steps. 1. Fine-tuning an automatic captioning system to produce desirable labels. 2. Relabeling the images from our text-to-image training set with this automatic recaptioning system. And 3. Training the text-to-image model on the dataset consisting of the images and new captions. For our training dataset, we selected a subset of 10 million photos from the LAION2B and improved aesthetics dataset. We used a pre-trained I2T captioning model, Poly. As the model outputs are relatively terse and lack in detail, we first collected a small set of 100 manual captions from human raters and fine-tuned the captioning model on that set. We asked the raters to provide 2 types of captions. First, a detailed caption for each image, with these instructions. Describe what you see in each image using 1 to 2 detailed sentences. Second, we collected a short and less detailed caption for each image with this instruction. Describe what you see in each image using a single short sentence. With this small dataset, we fine-tuned Poly for 300 steps, using a learning rate of 4E5, dropout rate of 0.1 and a batch size of 64, mixing 50% short captions and 50% long captions for multiple copies of the 100 images, using a different fixed conditioning prefix for the short versus long captions. When generating captions from the fine-tuned model, we use the terms recap short and recap long to refer to generations conditioned on the short and long prefixes respectively. Overall, the captions produced by this bespoke model improve both of the issues above. Their distribution better matches inference time prompts and they contain much more detail to improve sample efficiency. Section Summary. Recent advancements in text-to-image models have shifted from using based methods to autoregressive transformers and diffusion models. Improving text-image alignment has been a key focus, with methods using strong encoders and pre-trained text embedders to enhance alignment. Other related work includes fine-tuning Poly to recaption the training dataset of a text-to-image model, augmenting multimodal datasets to improve image captioning and embedding models, and rectifying text-to-image alignment issues in diffusion models through lexical analysis and attention map modifications. The proposed method, Recap, involves fine-tuning an automatic captioning system, relabeling images with the new captions, and training the text-to-image model on the updated dataset. The training dataset consists of a subset of 10M photos from the LAION2B and improved aesthetics dataset, and a pre-trained I2T captioning model, Poly, is used. The captions produced by the fine-tuned model improve distribution matching and contain more detail, addressing previous issues. Section: Image Generation Model. We further refined our Stable Diffusion version 1.4 model by training it for an additional 250,000 steps. We used a learning rate of 0.00001, a batch size of 512, and a prompt dropout rate of 0.1. We trained both the UNet and weights of the model, using a balanced mix of recap short and recap long captions, as this combination yielded the best results. All the results we present are based on this setup. Recap, our model, can work with any sampling method, but for this study, we used DDIM sampling with 50 inference steps and a guidance scale of 7.5. We compared Recap with two other models, the original Stable Diffusion version 1.4 model, baseline, and alt-text. Alt-text is the baseline model, but fine-tuned with the same parameters as Recap, except it uses original captions instead of Recap captions. We evaluated the models using automated metrics, human evaluation, and a qualitative assessment of examples. Across all these evaluations, Recap showed improvements. For automated metrics, we used a set of measures suggested by previous researchers on the MS-CoCo validation dataset. We found that images generated by Recap had a better FID score, indicating higher overall quality. We also evaluated the model's ability to accurately generate requested objects, count the number of generated objects, correctly position objects, and adhere to the prompt. In all these aspects, Recap outperformed the other models. We also conducted a human evaluation, where raters were asked to choose images generated by each model that successfully followed a given prompt. We used 200 random prompts from the MS-CoCo validation set and the challenging Drawbench dataset. We found that Recap had a higher success rate in generating images that followed the prompt, both overall and for each individual prompt. In terms of qualitative results, we found that Recap was better at interpreting relationships between entities. For instance, in the prompt, a pizza near a pineapple, while the base model placed the pineapple on the pizza, Recap correctly placed the pineapple near the pizza. Recap was also better at handling complex modifiers. In conclusion, our Recap model showed significant improvements over the baseline and alt-text models in all evaluation metrics, proving the effectiveness of our approach. Section Summary. The authors fine-tuned the Stable Diffusion version 1.4 model using a combination of Recap short and Recap long captions, resulting in improved performance across various metrics. Human evaluation showed a significant improvement in successful image and prompt generation compared to the baseline model. Qualitative results demonstrated that the Recap model better interpreted relations between entities and handled complex modifiers more accurately. Section. Analysis. We believe that the enhanced quality of image generation, as seen in our results, is due to two key improvements in the training captions. 1. Minimizing the difference between the training and inference prompts, and 2. Providing the model with more text information per image, thereby enhancing the efficiency of the training sample. We'll demonstrate through an ablation analysis that our Recap captions achieve both these improvements, and that the resulting model benefits from both. Let's compare different types of captions. We've compared the captions generated in the training set with those in the MS-CoCo validation set, using various language metrics. We used MS-CoCo as a representative of the prompts we expect to see during inference. Our findings show that our generated captions are more similar to MS-CoCo in several ways. We used standard language metrics from the TextStat Python package to compare them, calculated over 10 million examples in each training dataset. The Flesch Reading Ease score, a standard measure of text readability, shows that Recap generates easy-to-read sentences, while the original alt-text is often difficult to read. Similarly, the text_standard score, which estimates the minimum grade level required to read the text, shows that Recap generates texts that a fourth grader can read, while the original alt-text requires an 8th grader to fully understand. To directly measure the reduction in training inference skew, we compared the distribution of the embedded texts. We calculated the Frechet distance between the embeddings of the various datasets, using Stable Diffusion to encode the text. As we suspected, Recap-generated captions are closer in distribution to the MS-CoCo captions than the alt-text captions. Moreover, the Recap short captions are closer to MS-CoCo than Recap long captions. These results align with the improvement in FID of the images from models trained with the corresponding datasets. Next, we evaluated how well the automatically generated captions describe the images. We asked raters to score each caption for 100 random images, considering both faithfulness to the image and completeness in describing the image, on a scale of 1 to 5. Recap-generated captions were rated as more faithful and complete than alt-text captions. This supports our belief that automated captions make training more efficient by providing more text information. We then compared the results of fine-tuning Stable Diffusion on our two caption types, Recap long and Recap short. Training on Recap short captions achieves better FID scores, and faster, but with little semantic improvement, while the recap long captions show significant semantic improvement. Mixing the caption sets, Recap Mix, provides the best of both worlds. The improvement in FID on the MS COCO validation set is correlated to the improvement in the fretchit distance of the generated captions. This suggests that the semantic improvement in the recap long model comes from improved training sample efficiency, not just from reducing the training inference skew. To further explore the contribution of the improved examples to each part of the stable diffusion model, we compared training only the UNet weights versus the weights versus both, using the same training and evaluation procedures. As expected, training more weights achieves better performance. Interestingly, training only weights, which are about 12% of the total weights, achieves better FID, with fewer training steps, but with little semantic improvement. Training both and UNet weights results in significantly higher improvement to semantic scores than training only on one of them. We believe that training weights mainly reduces the skew in the distribution of text between the training set and the evaluation set, while training the UNet weights mostly improves the alignment of the text to the image. Section Summary. The improvement in image generation quality is attributed to two factors: reducing the discrepancy between training and inference prompts and providing the model with more textual information per image, which enhances training sample efficiency. The generated captions from the recap model are closer in distribution to the MS COCO captions, are easier to read, and are rated as more faithful and complete in describing the images compared to the original alt text captions. Training on recap short captions achieves better FID scores and faster training, while recap long captions exhibit significant semantic improvement. Mixing the caption sets, Recap Mix, provides the best overall performance. Training both the UNet and weights of the stable diffusion model results in higher improvement in semantic scores compared to training only one of them. Section Summary and Discussion. In this study, we've demonstrated how the performance of text-to-image models can be enhanced by training them on artificially created captions. Our detailed analysis shows that brief descriptions that minimize the gap between training and inference are beneficial. Similarly, lengthy and comprehensive descriptions that boost sample efficiency, despite their difference from the inference set, are also advantageous. We've also shown that incorporating these varied descriptions into the training set can improve performance on multiple levels simultaneously. Looking ahead, there are several intriguing possibilities for further research. For instance, we could explore whether refining the captioning model to provide abundant detail in specific areas could enhance semantic capabilities in new fields. Could we, for example, develop models that accurately generate hairstyles, room layouts, facial expressions, clothing, and so forth based on detailed descriptions? Another potential avenue is to use our recap method to train text-to-image models in areas where textual captions are absent, such as personal photo albums or TV show screenshots. Our preliminary experiments in this area show great potential. We've also experimented with fine-tuning a model using recap captions, but it would be interesting to compare this with a model that was trained from scratch on recap captions. Additionally, we could experiment further with different combinations of the three types of captions we've used: recap short, recap long, and alt text. More broadly, we could consider creating and blending several more types of recaptioning models. This could help us bypass the token limit by training on the same image multiple times, each time with a different portion of the caption. Regardless of the token limit, it might be worthwhile to investigate training on several shorter captions per image instead of one long one. We could also explore the impact of recap on larger models trained on larger datasets. Finally, as recap underscores the value of high-quality datasets and shows that they can be enhanced with synthetic data, we hope this will further motivate the application of such techniques beyond the text-to-image domain.